interplay between quantum information and classical information, and new functionalities that only make sense in a world with quantum information and qubits. As a reminder, if you have any questions, it would be best if you could wait for the assistant to come around with the microphone just to make sure that everyone can hear you. Our first talk today is actually a merger of two accepted talks. It's about unconditionally secure commitments with quantum auxiliary inputs and or preprocessing, and Barak is going to start off by giving us the first half.
All right, thanks. As said, I'm Barak Nehoran, and this is based on joint work with Tomoyuki Morimae, who is here, and Takashi Yamakawa, as well as concurrent work by Luowen Qian, who independently arrived at the same result and will give the second half of this talk. So this talk is about quantum commitments with auxiliary inputs, and I'll talk about that in a moment. But first, I know we're all from different backgrounds with different terminology, so I want to make sure that we're on the same page with what we mean about unconditional security. So unconditional security is often associated with terms like information theoretic security, statistical security, and true love. Okay, maybe not that last one, since I'm pretty sure we're talking about cryptography here. Sorry, guys. In any case, unconditional security is a distinct concept from the other two, which are in fact closely related. And for this talk, it's actually crucial to understand the distinction. So let's get into the specifics. You can put them to sort of chart like this. And at this point, if you're familiar with these terms, you might have the urge to just doze off. But please bear with me for a moment, because otherwise you might be really confused when I talk about cryptography that satisfies one notion and not the other. So information theoretic security, as opposed to computational, indicates that you're secure against any adversary, supposedly because the adversary just won't have enough information. This is nice, of course, in many ideal scenarios, but it's not always possible to achieve. Sometimes we have to settle for computational security, where we choose some specific type of adversary that we deem to be efficient and show that this particular adversary can't break our security because of its limited resources. Now, the proof of security can take one of two possible forms. We can have security reduction, where the security holds conditioned on something else being secure. Or in the best case, we can prove security outright with no conditions. So the catch is that nearly all proofs fall along the diagonal of this table, either an unconditional proof of information theoretic security, like one-time pad or quantum key exchange, or a conditional proof of computational security, where we choose a specific adversary and show security reduction to a hard problem. So classical key exchange follows here, as does all of computational cryptography. And this is why the term unconditional security is so often confused with information theoretic or statistical security, because for most cases, these are just come in hand. And in fact, it's hard to find examples of any schemes that fall outside this diagonal. Security proofs up here do exist, but they're quite rare and usually not necessary. And on the other side, if we could prove security if we could outright prove the security of any computational cryptography, that would bring it down here. But unfortunately, there are barriers to doing this, and computer scientists have struggled to get around them. For classical cryptography in particular, this would require showing that P doesn't equal NP. So we do have things like the existence of hard-to-compute functions, which is like either hard to compute or hard to invert, whichever one you want. But there's nothing computationally useful here. So nothing cryptographically useful here. So can we get unconditional computational cryptography? So our works show for the first time a commitment protocol that falls in this category, specifically when all the parties receive a quantum auxiliary input. So commitment schemes allow someone to lock away a message that they can send to someone else and later reveal the message without being able to modify the message that was committed. And commitments with quantum auxiliary inputs were first defined by a work in 2016 and allow all parties to receive a quantum advice state as input. And the CKR construction showed the security from a computational assumption. But we show perhaps surprisingly that no computational assumption is needed. In other words, they exist unconditionally and with computational security. And to the best of our knowledge, this is the first example of a cryptographic protocol where the security is inherently computational but is unconditionally secure against polynomial time attackers. So I'll start by motivating why we care about quantum commitments. Then I'll define quantum commitments, including those with auxiliary inputs. And then I'll recap our results and pass it on to Luowen, who will tell you more about them. So let's start with why commitments are so important for us to study. And the reason is that commitments can be viewed as a necessary assumption for cryptography to exist. So classically, we can, if we look at the big picture on computational cryptography, it looks roughly like this, with the implications between all the different cryptographic primitives, all leading down to one-way functions at the bottom, as well as everything equivalent to them, including commitments and so on. And because of this, the existence of one-way functions and commitments was considered the minimal assumption without which cryptography could not exist. And having secure one-way functions at least requires that P doesn't equal NP, which there are known barriers to proving. In the last few years, however, a line of works on cryptography with quantum states has shown that this is not the full picture. And in fact, there is a whole world of quantum cryptography below one-way functions, which may exist even if P equals NP, all leading down to quantum commitments at the very bottom and everything equivalent to them. So back in the 80s, when it was discovered that quantum key agreement could be made unconditional and computationally and statistically secure, there is hope that we can do the same thing for other quantum primitives like commitments. Ultimately, we now know that commitments can't be statistically secure. They must be computational. But there's no reason why this computational security can't be unconditional. And this is one of the my main messages for you, that there's nothing preventing us from proving this. There's nothing preventing us from doing this, since it won't imply that P doesn't equal NP. And so the known classical barriers aren't really an issue. As it currently stands, we don't have any barriers against it. And quantum commitments with their position at the very bottom are a prime target for this, so the lowest hanging fruit, so to speak. So our proof that it is possible when all parties receive quantum auxiliary inputs, notably despite the classical barriers, may give us hope that we can do this in the plane setting as well. Okay, now let's define quantum commitments as well as the variant with auxiliary inputs. In the quantum case, commitments in their most basic form look something like this. So you have two quantum states representing a commitment to either a 0 or a 1. And you can ignore one of these states for now, just look at the first one. And each one of these, like this state is on two registers, D and C, that are entangled to one another. And the C register is like the locked box containing the message, and the D register is like the key to opening it. For those who are wondering, I'm depicting them in what's called the Schmidt basis, because I find that's the most intuitive and visual way to depict entanglement, where we just have superposition over all the different connecting segments. And note that I'm only going to talk about non-interactive commitments, but if that bothers you, then feel free to rest comfortably knowing that this is without loss of generality, because every commitment can be framed this way. So how do they actually make a commitment with these states? So say Alice wants to commit to the bit 0, so she chooses the first state and sends the C register to Bob, and that's called the commit phase. Later on, when she wants to reveal her commitment, she sends the D register to Bob, at which point he can see that it was committed to and can verify that it's valid. And the security is about what happens in between the phases. So Hiding says that in Bob's view, he cannot tell whether Alice committed to a 0 or a 1. And Biding says that Alice cannot act on just her view to change her mind about which one she committed to. And commitments with quantum auxiliary inputs is just the same, but where both parties have access to copies of a fixed quantum state, which may not be efficient to prepare. And Alice can download as many copies as she needs, which she can use to prepare the entangled state, and then she can use to commit to Bob, and at any point they can download additional copies, but don't need to, until the reveal phase when Bob can download more copies to verify the commitment. So now I'll finish with a quick overview of our results and pass it on to Luowen. Okay, so to recap, we show, wow, these lovers really are committed, huh? So we show that these commitments exist unconditionally, with computational hiding and statistical binding. So recall that I mentioned that they were originally constructed from a computational assumption, namely that QIP is not contained in QMA. But surprisingly, we show that this assumption is not necessary, or really any assumption for that matter. We just prove it outright. And with that, I'll pass it on to Luowen.
Okay, thank you, Barak. So for the second half, I'll be telling you more about the commitment construction analysis, and then I will wrap up. Okay, so I'll just begin by defining auxiliary input commitment more formally. But before we go there, let me first tell you the classical version, analog of this, which is the classical auxiliary input commitment. And this is actually a notion that was already considered by classical complexity theorists and cryptographers, like as early as Ostrowski and Wilkerson in 1993, where they defined this kind of object. Yeah, and as Barak said, basically the idea is that they can do some inefficient preprocessing to find some inefficient classical string in the classical case, and each of them will have some classical string. And notably, it's not too hard to show that even in this setting, if you have a secure commitment unconditionally, then you will also prove P not equal NP. So there is still the barrier, even if you allow classical auxiliary input. Yeah, and just to be clear, the adversary can also do arbitrary preprocessing before the attack. Before the protocol. And the difference between classical and quantum is just that instead of each of them preparing a classical string, now they have prepared some inefficient quantum pure state. And our main theorem formally says that unconditionally, there is a quantum auxiliary input commitment scheme with inverse exponential security error in the security parameter that satisfy one, it is statistically binding against unbounded committer or Alice. Second, it's computationally hiding against any receiver or Bob up to exponential size quantum circuits, including possible quantum advice. And let me also explain why the title has preprocessing in it. That's because in addition to the quantum auxiliary input model, we can also further tell you how to actually prepare these pure states, well, not efficiently, but in doubly exponential time. So you can always prepare it in doubly exponential time, and you can even improve it to single exponential time if you are willing to assume BQP equals QMA, which is okay because our security proof is unconditional, so it doesn't contradict anything. Alternatively, if you are willing to use exponential amount of communication, you can also reduce the time from doubly exponential to single exponential. Okay, before telling you the construction, let me just quickly talk about applications of commitment. So Barak already showed that if you have a quantum commitment, you can do other stronger applications like oblivious transfer and MPC, or zero knowledge. And we showed that, yes, with a quantum auxiliary commitment, you can also do these applications with basically the existing constructions. So in Barak's et al.'s work, they show how to further use this to do quantum auxiliary input zero knowledge proof for NP with non-uniform simulators. And in my work, I show a different application called quantum auxiliary input secure multi-party computations, but the simulation error is only epsilon simulation secure, and the simulator is also non-uniform. Yeah, don't worry too much about the caveats if you're not familiar, but essentially you can do more or less the same application that you can do. Okay, now let me talk about the construction. So the construction is going to say that, proceed that by following. First, I'm going to claim that there exists some good function, 0, 1, so it's like mapping lambda bit input to 3 lambda bit output. So let's say I just take the lexicographically smallest function that is good. And by good, for now, you can just think of the meaning of good being if you use this function, this construction will be secure. Okay, so it is some classical exponential size function, or polynomial size input, but the truth table is exponential size. Okay, so the two commitment states are follow. Only the commitment state to 0 will be using this hash function. So it will have x on uniform superposition of x on one register, and then h of x on the other register. So yeah. And the commitment state to 1 is just the uniform superposition over yy for all possible images. So yeah, so the second state you can actually prepare efficiently because it's just the maximum entangled state. And the first state you need to prepare it, you need the knowledge of this function h, which is exponential, has exponential size description. But the length of this auxiliary input is just 4 lambda qubits, which is efficient. Okay, yeah, and as Barak said, we are going to use this template where to commit, you are just going to send the O register of either the 0 state or the 1 state, and keep the P register to yourself, and to reveal, you send the other register. And to check that the receiver, if he wants to check if the state is correct, you just do a swap test. So if I claim I committed to 0, you do swap test with 0. If it's 1, then you do swap test with 1. Okay, so that's it. That's the whole construction. So the main theorem that we show, or the main lemma we show here, is that if you just pick a uniformly random function as your h, then it is actually good, meaning that this construction is secure with overwhelming probability, which means that such a good function exists. Okay, so to tell you a little bit about the proof, let me talk about computational hiding. So for computational hiding, well, essentially what we want to show is just that for a random function h, the output of the function h, which will be corresponding to the thing you will see when I am committing to 0, is indistinguishable from a truly uniform random 3 lambda bit string. Yeah, this is so this is exactly what we want to try to prove. Okay, so it turns out like this is a pretty well-studied problem. Classically, it's called sparse pseudo-randomness, and we want to try to prove a post-quantum version of this. And we want to prove that this is secure even against exponential size circuit with exponential size advice. Okay, so in our paper, the way we prove this is by invoking some security techniques that was developed in proving non-uniform QROM security, where the QROM is just like a random oracle model where everyone can make quantum queries to. And I want to say that these techniques are really very general, and you can prove very strong things with it. But a slight downside is that the proof that the exact constant you get, like the asymptotics you get, is not optimal. So after we have this paper, Fermi told us that there is actually a more algebraic proof, like that's more primitive. And the idea is that it's actually very similar to the classical proof of proving this, which is like using some type of Chernoff bound. But for quantum circuits, rather, you would use a matrix Hofstein bound. And I think it's slightly less general, but you get a better security. So you get only square root loss instead of cube root loss. And this matches the best known classical attack, which achieved the same success probability, where S is like the size of the circuit that you are trying to use to attack the scheme. Okay, so in our paper, okay, so sorry. So going back, what we show is that quantum auxiliary input commitment is indeed unconditionally possible, as long as you are willing to use the quantum auxiliary input or some pre-processing phase. Okay, so one natural question you may ask is this really impossible classically? So I did tell you that classical auxiliary input commitment is impossible without P not equal NP. Maybe you can ask, what about classical randomized auxiliary input? Because here we're using a pure state. So maybe to give classical cryptographic protocols a fighting chance, maybe they should use a randomized auxiliary input as well. Okay, so so essentially here, the model we want to think of is that they are thinking about the same distribution, and each of them will draw a sample from the same distribution. And what I show is that as long as you have sampling access to this distribution, you cannot have unconditional security without also settling P versus NP. There is also a related randomized auxiliary input model called secret parameter. So here, the two parties actually get some correlated string. So instead of getting the same string from a possibly different string from the same distribution, now the two strings can be totally correlated. I should note that in this model, even statistical commitment is possible, but the Barak and our paper show that it remains impossible as long as the correlation is small enough. Okay, so we also give some additional result that shows that you can actually adapt our protocol to a completely efficient setting if you are willing to have some weakly trusted state distributor whose only job is just to hand out pure states. And once you are willing to go to this model, then you can get a completely efficient, but there is a very weakly trusted third party that helps you to do this commitment scheme. Okay, so let me just wrap up. So in our two papers, we gave the first demonstration of a useful cryptographic task with unconditional security that is inherently computational. And again, this is the first one, no matter you think of just quantum or either classical or quantum. So my interpretation of this is like a glass half full, half empty situation. So if you are optimistic, maybe you should think of this work or these two work as showing like maybe this is the beginning of trying to prove unconditional computational cryptography, especially quantum cryptography. But on the other hand, maybe as you can see from the construction, it looks like the unconditional security really relies on having access to this quantum auxiliary input. So if you are pessimistic, maybe you will say that, okay, I don't really see a way to build this without using quantum auxiliary input for any other thing. But no matter what you think, I think we should all agree that we should reassess the necessity of computational assumptions for cryptography, especially quantum cryptography, as well as the existence of barriers for establishing unconditional cryptography. Yeah, that's all. I'll take some questions. Yeah, either a question to me or Barak.
Thanks for the talk. Could you explain what you mean by computationally hiding against exponential size circuits?
Yeah, basically what we show is that it's this security bound that I showed you. Okay, I can't find my mouse, but like essentially like the security, something you can show is that up to quantum circuit size 2 to the 0.1 lambda, your best chance of succeeding in breaking the protocol is like 2 to the minus 0.1 lambda, something like that. So you have exponentially small success probability up to some certain exponential size quantum adversaries.
I see. So it's not like against Pauli size, but some fixed exponential
Yeah, it's a
size.
fixed exponential. It's not all exponential.
Maybe one more question if it's quick. Okay, we can stop here.
Oh, one more. In the front here.
Okay, so regarding like similar results in the classical setting, what about the random oracle model? Aren't there like very similar, like the take-home message isn't it kind of similar to results saying, yeah, in the random oracle model, there exists one-way function, and the take-home message there isn't that we should look for one-way functions which are, even though there are no barriers, but we do have similar results like that, right? Like say, if we have random like in the random oracle model, for example, there exists a symmetric encryption, right? Results like that. So I'm not sure if it's
Yeah, I mean, you could. Yeah, that's certainly one way to one perspective to view this is like, maybe this model is not this model doesn't necessarily mean something that we can build unconditionally in the plain model. But on the other hand, this is definitely interesting because this is something that you can actually implement if you had exponential preprocessing, as Luowen said. So
Yeah,
it's kind of different in that sense from the random oracle model.
Yeah, I think it's a fundamentally different model because we don't live in a random oracle model. Like, I can't query a random oracle, but I can do exponential size preprocessing.
Okay, thanks.